I guess the blackboard is visible, right?
Yes, sir.
Yeah, because in my
Yes, sir.
in my team, nice to hear the girl's voice as well. So, in fact, it is not showing in my screen here in my Teams app. But I mean, if you can see, that is good enough for me. Okay. So today, and probably in my next class also, throughout, I'm going to be using the blackboard only. I hope it is going to be at least better during my recordings. Okay. Fine. So now you can see that I have already written down the uniqueness and existence theorem in the blackboard. Okay, so now if you go through this, so I'm going to call it theorem A, and it is due to Picard, and there are many variants of this theorem. Okay, you may come across Piano's theorem. I'm definitely going to give you the statement of Piano's theorem because this is part of your syllabus later on. So, but let me guarantee you that the way I am going to prove this theorem here, you will be able to prove any variant of this uniqueness and existence theorem. Okay, so you don't need to worry about anything. Fine. So now let us see what is being, stated here. You have come across this, emptied a number of times. So what it is saying that f of x comma y and its first order partial derivative with respect to y are continuous functions of x and y on a closed rectangle R. I'm going to draw it, don't worry about it, with sides parallel to the axis. If x naught y naught is an interior point of R, then there exists a number, of course it is a positive number, is strictly greater than 0 with the property that the initial value problem given by the equation 1, and later on also I am going to refer to it as simply equation 1. Okay, so if I say equation 1, it is simply going to represent the initial value problem, which is written here in the blackboard. Okay, even without writing it, if I don't write it down, you should assume that it is exactly that one. Okay, so it has only one and only one solution, y equal to y of x in the interval x minus x naught less than equal to 8. So basically we are going to consider a closed interval along x-axis. Okay. So now let us try to visualize it, how it is going to look like. Okay. So this is x, this is y. Okay. And let me consider. This as my region R. Let me consider this as my region R. Okay, because they haven't given me any like say range of x and y in R. For the time being, let us not worry about this. So this is simply the region R. Okay, and we have also been told that. And remember, whenever you have to prove something, some theorem, what you have to do at the very beginning, look at the inputs. Okay, what are the information you have there in the theorem so that you can utilize them to prove it. Okay, so here another information that we have been provided is that your x naught y naught is an interior point. Okay, fine. So like say suppose this is x naught, okay, and when they talk about this interval is nothing but it is going to contain all x in such a way that x lies between x naught minus h and x naught plus h, of course including the boundary point. So suppose I am thinking about something like this. I'm thinking about something like this. So this is x naught plus h. This is x naught minus. Is it okay with everybody? Fine. So this is this equation, and we are trying to find some solution. Of course, that will come later on. So something like this, which passes through this point. Okay, which passes through this point. Okay, so Suppose this is the solution for y equal to yx. Is it clear? Fine. At least we have been able to visualize the statement here. Okay, the proof will come later on. Fine. Okay. So now let us move step by step, and I'm going to go a bit slow, and maybe it's going to take me, may take me more than 2 days. Okay, but I want this to be permanent in your brain. Okay, fine. So now let me start with daily proof. Okay. So you know that if yx is a solution of this differential equation, yx not equal to y naught 1. Okay, so then if I can have an integral equation of this form, if I have an integral equation of this form, which gives me, fine, let me call it 2. Okay, so you know that every solution of 1 is also a continuous solution of 2. Is it okay?
Yes, sir.
Fine, because we have already proved the equivalence of those two statements. Okay, so now in order to prove that the equation 1 has a unique solution in the rectangle R under the prescribed condition, if we can prove that equation 2 has a unique solution in the rectangle R, then our job is done. Fine. So that is exactly what we are going to do. Is it okay? Fine. That is exactly what we are going to do. Okay. So basically, what we have to do, we are going to find a unique solution for the equation 2 in the interval given by this. Okay. And for this, because see, they still haven't told me anything about h. Okay, so basically we should be able to find some h strictly greater than 2. Okay, which will enable us to find a unique solution of equation 2 in the interval given by this. Okay, and let me tell you that for the proof I am following Simon's book. Okay, for the proof I am following Simon's book, and I am going to explain the things here, and I may not be able to write down all the things systematically. So what I suggest to you is that you just note down everything, whatever I am going to write in the blackboard, and later on through my recording, you will be able to understand what, even if in the class you are not able to follow something, hopefully you'll be able to understand through the recording what I was trying to say. And then what you do, you take help of Simon's book and you please write down the proof on your own systematically. That is going to be of great help. Okay, fine. So, so far so good. So this is only the very first step. Okay. So now what we are going to do, because you have already seen some evidence. You have already seen some evidence that if I can generate a sequence of functions, if I can generate a sequence of functions y and x and going from 0 to infinity, defined by your y naught x equal to y naught, y1 x equal to y naught plus x naught x f t, y naught t dt, y2x equal to y naught plus x naught x f t y1 t dt, and y and x equal to base dy n minus 1 p dt and so on. And let me call this sequence of function as A. Okay, so you have already seen, I mean, in Picard's method of successive approximation that, I mean, if you are told to find the solution of a initial problem like this, then by generating a sequence like that, sequence given by A, we can make the sequence converge to the solution of the given differential equation. Okay, fine. So that is what we are going to do. That is what we are going to do. We are going to prove that the sequence given by A, it converges to a continuous function y of x in the given rectangle R, which contains the interval given by x mod of x minus x naught is less than equal to h. So that is what we are going to do. Okay. Now, here one thing to be noted is that let me tell you what that is. Okay. So far we have I have given equation 1, 2, and A. Remember, equation 1 is the original differential equation. Equation 2 is the equivalent representation by the integral equation of the solution, and equation A contains the sequence that we have constructed out of the equivalent integral equation. Okay, fine, something like that integral equation. Okay, fine. So now if you look at the sequence, then I can write, say, y and x okay, fine. Is it okay with everybody?
Yes, sir.
Yes? Okay. So you may be thinking, why I am writing this in this form? Okay. Now, I can say that this y and x is nothing but the nth partial sum of the infinite series given by your y naught x plus your I going from 1 to infinity yix minus y minus 1x. Is it okay?
Yes.
Yes, fine. So basically,
Yes.
fine, we have an infinite series given by this. Maybe we can call it B. We have an infinite series given by B, and each term in the sequence given by A is nothing but the nth partial sum of the infinite series given by B. Okay, fine. Okay, so
Sir,
now,
this range is I to n or infinity?
which
Summation
one?
summation
No. See, this is an infinite series. That is why its range is 1 to infinity, right? But this one is the nth partial sum of this infinite series. If you curtail this infinite series, instead of say, if instead of infinity, you simply plug in n, then you are going to get y and x, isn't it? That is nothing but the definition of nth partial sum. Is it okay?
Okay, sir.
Fine. Okay.
Fine.
Please ask me question. If you have some doubt, please ask me so that I can clear it up. There is no hurry. Okay. Fine. So now And can you tell me how did you prove the convergence of an infinite series?
If nth partial sum series is convergent, then convergent.
Exactly. If the sequence that has been extracted out of the nth partial sum, then the infinite series is convergent, or vice versa. Fine. So
Yes.
what we are going to do here, we are going to prove that this infinite series converges to some function yx belonging to the interval S. Is it okay? That is what we are going to do. Okay, fine. Okay. So see, we still haven't produced the number h. Where is h going to come from? Okay. So now this theorem is going to be proved in 3 steps. This theorem is going to be proved in 3 steps. Let me try to give you the 3 step. Okay. So after we produce your h greater than 0, so that we can define an interval like this. What we are going to do, these are the 3 steps that we are going to do. So maybe now I can erase this also, because now we have all the information required. So based on that information, we are going to do. So the steps. Number 1. Okay, number 1. So this series V converges to some function yx. Okay, fine. Then number 2. Okay, it is not enough that it converges, but I have to prove that this yx is a solution of the integral equation 2. Fine. Is a not only any solution, it has to be a continuous solution of equation 2. Okay, and then we have to prove that this is the only solution. Is it okay? Then number 3, we have to prove that yx is the only continuous solution of 2. That's it. Okay, so now you know what we'll have to do. Basically, these 3 things we'll have to do. Is it okay? Fine. So now let us try to proceed. So firstly, what we are going to do, we are going to firstly find that h. We are going to thank you. So we are going to find that h, and then you will see that some of the ideas, at least one of the ideas, it will seem to be very wild, but you will see that that is going to work, fantastically well later on. Okay, so that's what we are going to do. And let me tell you, okay, maybe let me find h greater than 0 first, and after that I'll give you some idea about how we are going to proceed, and then we are going to actually proceed. Okay, fine. See, we have been given that your f and we have been given that they are continuous in R. Okay, they are continuous in R. Is it okay? Fine.
Yes, sir.
And this R, we are assuming that it is a closed rectangle. Okay, and you know that every continuous function in a closed interval is bounded, isn't it?
Yes, sir.
Fine. And here, of course, the interval along x-axis is given by. Okay, fine. So that h I still haven't found because I'm going to find it from here. So therefore, there exists your positive numbers m and k, such that your f of xy, mod of f of xy less than equal to m, okay, and mod of del f del xy, this is y less than equal to k, and this will happen for all your xy belonging to that rectangle R. Is it okay?
Okay.
Yes, sir.
Fine. Okay, fine. So let us maybe should I number it? Anyway, you will remember. So I had 1, 2. So maybe I can call it 3. I can call it 4. Okay, fine. Now, okay. So, okay, this is x, y. Okay. So now let us consider 2 points. Let us consider 2 points. Your xy1, okay, and xy2 in R. In R, say suppose this is R. Suppose this is R. Okay. Along this same vertical line. So basically, say suppose this is x. Okay, this is x, and then what I am doing, I am considering like 2 points. Say suppose this is xy1 and this is xy2. Is it okay? Thanks. Just something like this. This situation is something like this. Okay. So then what we can do, if I try to find your f of x y1, xy2, right? So because I have a fixed x here, okay, fine, x is not varying. I am assuming that I am taking it along the same vertical line. Okay, so then I can consider both of them simply to be function of y only, or forget about it. Even if it is a function of both x and y, then because I am keeping x fixed, so I can think about the partial derivative of this function with respect to y, because I am not varying x. So if I use mean value theorem, so this is going to give me your del f del y x and some y star at some point y star into your fine.
Yes, sir.
Yes. Okay. Fine. So this is equal to your del f del y. Of course, this is where y star lies between y1 and y2. Okay. y2, and then
This is less than k into y mod of y minus y.
yes, fine. This is k, and this I have found out from this relation number 4. Fine? So far, so good. Is it okay? And this I'm going to use extensively, this relation also. Like basically this relation. So f of, I mean, even you don't need to worry about it. This is going to come, I mean, quite naturally. Let me call it 5. Let me call it 5. Okay, fine. So now let me come to choosing 8. How we are going to choose 8? Okay. Now, we choose 8 such that your K8, of course, we choose 8 such that H is greater than 0 and K8 is less than equal to 1. Okay? Fine? Say if you have any problem, or like say, do you have some doubt? I mean, why can we choose 8 like that? See, basically, I mean, whenever we are thinking about these two, I mean, inequalities, basically it is giving bounds for those two functions, right? F and del f, del y. Okay, fine. And these are big numbers. I mean, we assume that they are big numbers. Okay. Whatever big they are, say k can be a big number, like say maybe 100, right? But we are going to choose 8 to be so small, that their product is always going to be less than or equal to 1. That is always possible, isn't it? Yes?
Yes, sir.
Yeah.
Yes, sir.
That is always possible. So now, my next statement is going to be very, very crucial. My next statement is going to be very, very crucial. Okay? So now, the choice of these 8 is going to allow me to define a sub-rectangle, R prime inside this rectangle R. Okay? Let us see how we are going to do it. Okay? So I'm going to draw a figure. So after choosing 8 in this way, what we are going to do, we are going to find out, we are going to consider this sub-rectangle. R is something like xy belonging to R. This is the original rectangle belonging to R, such that you write it after this, such that your x minus x naught less than 8 equal to 8, and this statement that I am going to write down, this is very crucial. This. Okay, see, I choosing 8 arbitrarily small, I can always get intervals like this, or because I know that I am choosing 8 for my x interval, but the choice of this 8 is giving me an interval around y0 along y-axis. Interval around y0 along y-axis also, and this is always possible. Because if I choose h very small, I can always get a sub-rectangle. I can always get a sub-rectangle R prime like this, isn't it?
Yes.
Okay.
Yes, sir.
Okay. Let me just try to give you a pictorial explanation for this. Okay. Let me try to give you a pictorial explanation for this. This is my R. This is my original rectangle R. Okay, and suppose this is my point. This is my point x naught comma y naught. Okay, fine. So now this is x naught. This is y naught. Okay, fine. So now what I'm going to do, say, suppose this is x naught minus 8, this is x naught plus 8. Better. Okay, fine. And suppose this is y naught minus mh. This is y naught plus mx. Okay, so that means if the bigger rectangle, this is R, then this is my rectangle R prime. Now is it clear? Right? Because if we choose H very small, I can always define R prime to be such that it is always included inside R. Fine?
Yes,
Any
sir.
doubt? Right? Because I am going to choose H very small such that I am always going to get a subrectangle R prime which is enclosed inside R. Fine? Yes.
Sir, sir, here our H's depend on K and M also, I think.
Yes,
Or-
kind of. Yes. Not really. H definitely it depends on K. Yes.
Sir, but sir, if M is so large, then M into H is which make our sir.
Ah.
If my question is, sir, like if it is depend on M or not, sir.
It will depend on M also. Yes. It will depend on M. Basically, later on, I'm going to tell you that it is going to depend more on M than K. Okay. But you simply think about, I mean, if you say, suppose, if you want to ignore the existence of M and K, say, for the time being, okay? So you simply think about H to be an extremely, I mean, small positive number, okay? Extremely small positive number. And now, let me, just a minute, let me think it that way. Yeah. I'm not sure, but I hope it is going to work. Say, suppose max of M and K, it is given by M naught. Fine. So if I choose my H to be even less than this, I think this is going to work. Is it okay?
Yes, sir. Yes, sir.
Fine. I think this is going to work. So we will always find a way to do that. Fine. Okay. So pictorially you have understood, and you please please draw everything, because later on in the book they have just simply given one picture. Okay. I want you to visualize things. Then it will be more permanent, and I can guarantee you that you are going to understand it better. Okay. So far so good. I still haven't proved anything. I'm just giving you information after information. I am simply constructing the proof. Okay, these are the steps to construct the proof. Okay, so now I am going to come to the real thing. And again, another thing, what I told you that I'm not me. In fact, I don't know whose proof is this. It may be, I mean, Simon's proof. I don't know exactly who proved this in this way. Because you are going to find, and yeah, and another information, probably you have received my email some 1 hour back, right? Or you didn't check? Yeah, somebody has checked. Anyway, so I have already uploaded the Codrington's book. You please download it. And Codrington book, you will find a lot of theorems on existence and uniqueness. But you will see that eventually everything boils down to the way I'm going to prove it. Okay, so if you follow me, I mean, properly, then you'll be able to do any kind of proof. Don't worry about it. Okay, fine. And I told you that some wild idea is going to give you some very smooth steps to prove this theorem. So that wild idea, in fact, it is about choosing the y interval to be something like this. Okay, that is why I'm telling you that the choice of h depends more on m than k. Okay, fine. So now I will come to the convergence. Now I will come to the convergence of the sequence given by A, which we are going to do it through the infinite series given by B. Okay, fine. Okay, so if you recall, y and x n equal to 0 to infinity. This was the series A, right? And then your so this was the series B, right? This was the series B. Okay, fine. So what I'm going to do, I'm going to prove that this series is convergent. This series is convergent, and it converges to a function y of x belonging to the subrectangle R prime. That is what I'm going to prove. Okay, and for that, you know that you know the concept of absolute convergence, right? Term by term,
Yes.
that's the convergence.
Yes, sir.
Right?
Yes, sir.
Right?
Yes, sir.
So in order to prove that this series is convergent, if I can prove the corresponding absolute series, if I can prove that the corresponding absolute series, let me call it B prime C, this series, if I can prove that this is convergent, my job is done. Fine. So let us break it down. This is, okay. So and since this y naught x is nothing but y naught, right? Because I have chosen my function y naught x to be a constant function. So basically, what I have to prove that this I have to prove that this series is convergent. Okay, fine. So now, again, remember, there is one thing. Yeah, I was hoping that somebody was going to ask me that question, but nobody asked me. So see, now if you look at this sequence. We are trying to prove the convergence of that sequence. Okay, so in order to like claim that the limit of this sequence, the yx, is the solution of the original differential equation, obviously what must happen? The sequence itself must belong to that rectangle R, or if it belongs to R prime, it is even better. Are you getting my point? See, only when all the terms of the sequence is going to belong to R prime, only in that case, I will be able to claim that. I will be able to claim that the limit of that sequence, y of x, it also belongs to R prime. Isn't it? See,
Yes, sir.
you may be thinking why I am saying this. See, because if I consider this, suppose this is my x naught, this is my x naught minus 6, this is my x naught plus 6. Okay, this is y naught minus mh, and this is y naught plus mh. So this is my subrectangle R prime. Okay, so suppose this is x naught y naught. Fine. Okay, so now obviously I know because the very first function in the sequence, it is given by y naught, right? So this is going to be my curve. This is going to be my curve, isn't it? This is going to be my curve, which is nothing but a horizontal straight line. And I surely know that these y, all the values of y naught x for all x lying in this interval, it definitely belongs to R prime. Clear?
Yes, sir.
Yes. But what is the guarantee? What is the guarantee that these y1x, y2x defined in the way that we have defined? It is also going to belong to this. Who knows? Like say, it may be so. It may be so that what is going to happen? Like say, my curve may look like this, right? For all the values lying in this interval, you can see that it has gone beyond this range, isn't it? I can have a situation like that, isn't it?
Yes, sir.
Fine. I want to see that this situation never arises. That situation never arises. For all x belonging to this interval, I am going to prove that firstly, all terms in the sequence, it lies inside this subrectangle R prime. Is it okay now? What I am going to do now?
Yes.
Fine. This is what I am going to do. Okay. So okay. So let me tell you how we are going to prove that. Okay, fine. Say for all x belonging to like say for all x lying in this interval, if you want to prove that this yx or just a minute. Yx is going to be in the subrectangle R prime. What we have to do? We have to simply prove that, or say ynx. Let me say ynx because they are nothing but the terms of the sequence, which are nothing but functions. If we have to prove that this ynx for all x lying in this interval, it contains inside R prime, what we must prove that this y and x lies between y naught minus mx and y naught plus mx. Is it okay? Fine?
Yes, sir.
Right? If I can prove that this happens for every value of n, then I can say that the sequence given by equation A, right? It belongs to that subrectangle R prime. Right? For that, what we must have proved? We must prove that y and x minus y naught less than or equal to mx. That is good enough. Is it okay?
Yes, sir.
Fine.
Yes, sir.
So once we are able to do this, then we will be able to claim that any points like x, y, and x, it is always going to lie in R. Okay, fine. In fact, this statement I shouldn't say this. So basically, I should say that if I can prove this way, then I can prove that any point this is going to lie in R prime. Right? Okay, let us try to do that. So obviously your this right, sorry, obviously this is simply equal to x naught y naught. This lies in R, right? Okay, this is obvious, fine. And then now let us see what is y and x minus y naught. Okay, and this is simply y and x minus y naught x. Okay, fine. And what is that? Or even this one, I don't even have to use this. I don't even have to use this. From the definition of y1 itself, it is going to come. What was that? See,
in general, we can prove that for yn.
yeah. But I want to go from y1, y2, etc. Okay, so that it is obvious to you. Okay, fine. See, because see, you may be thinking that okay, later on also the same thing is going to happen. In general, I mean, we can have only one singular expression. It may not be so. Okay, fine. So this is what? This is from definition. This is f t. Then isn't it? Fine.
Yes, sir.
Yes. So now
Yes, sir.
you see. So this is going to be. I mean, now what is happening? Your t y naught t, right? This is the point in R prime. Fine. This is a point in R prime. So that means it is a point inside the original rectangle R, right? So what we must have? So f of t y naught t, I mean, it must be less than equal to m.
Yes.
Fine. So from here, what I can say that this is less than equal to m, and then I'm going to write this only once, so that so that it is easier for you to follow. See, this is going to give me what? This is going to give me x minus x naught, isn't it? If I integrate it.
Yes, sir.
Yes, sir.
Fine, and that is less than equal to x. Fine, because my original interval for x is this. So that is why I can simply from here I can simply write it as this. Fine, although I am writing this only two step, but the inner steps were right like that. Is it okay?
Yes, sir.
Fine.
Yes, sir.
So
Yes.
that means, and again, like say I don't want to generalize it. I'm going to go step by step because you in each step you have to make use of the fact that now see what is this telling me? What is this telling me? From this I can tell that your y1x from here. What does it tell? So basically this is y naught plus mx, y naught minus mx, right? So that means it tells me now that the point x comma y1x it is going to belong to R prime. Is it okay? Fine.
Okay.
Yes.
And that is why in the next step I will be able to use this to be less than equal to m. Is it okay? See,
Yes, sir.
right? This has to be logical. Why I am doing it step by step? It is only because of that. Okay, fine. So now what you can do? If you now go to the next game, then by using this fact again I can do y2 minus y1x. So that is going to be x naught to x f t now y1t dt, right? Now, because from the previous step I have found this. Just a minute. Yeah, from the previous step, right? I have found this because from the previous step I have found that this very point, it belongs to R prime, right? So this relation is going to be valid, and from here again I am going to get mx and so on.
Sir, that is why not mode y2 minus y1. y2 minus y, that is
Oh,
why not.
sorry. This is why not, sorry. This is why not, sorry. Thank you. Fine?
Right.
Okay. I'm happy that you guys are concentrating really hard on the blackboard. Okay. So from here, obviously, now I can conclude that. Your this is less than equal to mh. Okay. So that all the sequences under consideration, they belong to that rectangle R prime. Fine. Okay, so that part we have proved. Okay, so now we are going to prove the convergence of the sequence. Okay, here we have proved the existence of the sequence in that, subrectangle R prime. Okay, so now we are going to prove the convergence of the sequence. Okay, so maybe I'm not sure I'm going to. So today's class is going to be kind of 1 hour. I'm not going to spend this weekend. To be precise, I'm just going to give you the hint what I'm going to do next. Okay. So now say, in order to prove the convergence of the sequence, I have already told you that I'm going to prove that it is absolutely convergent, right? Okay. So for that, what I have to do, this one, y1x minus. Maybe up to one step I have to do. Okay, so what I'm going to do, I'm going to convert it into a geometric series. Okay, fine. And from there, I'm going to conclude that this series is convergent. Okay, fine. Geometric series with some common ratio, and then my job will be done. And for that, what I'm going to do, now, see y not x. Okay, so this is simply y naught, right? See, this situation is something like this. Okay, so this is my subrectangle of this. So okay, so then this distance is your y naught. Okay, so basically I'm simply what I'm trying to see the distance of this line from the curve given by y1x. Is it okay? Yes. Fine. Okay, so obviously now what is going to happen? So at all points we are going to consider, right? At all points belonging to this interval, x naught minus x, x naught plus h, we are going to do that. So let us assume that, and let us assume that your max of y naught, this is equal to a, and that is for all x. Okay, fine. Okay, so then if I assume that, then I can claim from here that this is going to be less than equal to a. Fine?
Yes.
Is it okay?
Yes, sir.
Fine. So now see what we are going to do. I have to prove that I'm going to generate a geometry sequence, and for the geometry sequence, see, this is fixed. I don't need to worry about this. And for this one, I have already found out this is going to be less than equal to a. So for each term, I'm going to see what comes out. Okay. So for that, now what I have to do. So now next thing is going to be this. Okay. So now if I use, I'm just going to do it only once. If I use, so this is going to be this is y1, this is point from the definition of these sequences. Okay, fine. So now, obviously, this I can write as x naught x, and then ft y1t minus ft y naught t. Okay, fine.
Yes, sir.
Okay, so now let us concentrate on the mod of this. Let us concentrate on the mod of this. Okay, my blackboard is getting too small. Okay, so I hope you have already drawn it. Let me erase it. Okay, fine. See, let us work this out. See, f of t y1t minus f of t y naught t. So this is equal to, see again, for a fixed t, I am simply varying the values of y. Okay. Now, if you use mean value you have here, so then this is going to be del f del t, your t, something like y star, and then your y1t minus
Del f del y.
del u del y. Yes, because here t is equivalent to x, right? Okay. Is it okay with everybody? Because see here y is varying, so that is why I am going to take the partial derivative with respect to y. Is it okay? Fine. So then this was less than k. Right? This was less than equal to k, isn't it?
Yes, sir.
Because this point definitely this point t comma y star, it lies in R prime.
Yes.
Fine. And then this is say y1t, and because y naught t is simply y naught this. So now say I am doing it. If I do it for the whole interval, so then I can say that eventually this is going to be less than Ka from this relation. Is it okay?
Okay.
Yes.
Yes,
Okay.
sir.
So that is why again from here, once you take this out, the mod part, from there you are going to get Ka, right? And you will be simply left with mod of x naught x dt, and that is going to give you mod of x naught x minus x naught. So eventually I am going to get Ka h. Okay?
Yes, sir.
Fine?
Yes.
Okay. So now let me move to the next one. So I still don't want to directly jump onto Yn. See, so I have got, let me simply write it down. I have got y2x minus y1x less than this. Okay. So now, so then what is going to happen? See, the way I was working this out. So again, what is going to happen? Now, if I do y3, y2, so this is going to give me x naught to x, f t y2 t minus f t y1 t, isn't it? Fine. And again, for this one, I have eventually for this one. Just a minute. Sorry, just a minute. Fine. So for this one, I have this relation. See here, what I would have done. Now, if it is 2, it is 1. Then this is 2. This is 1. Fine. And here I am going to have y1t, y2t, y1t. Okay, fine. And then this is k, and from here
Square. H.
k
square.
This is KAH. Fine. Okay. So basically this is k square AH. Fine. So once I plug this in here, what I'm going to get eventually from this part, I'm going to have k square AH, and from the remaining part, x naught to x dt, I'm simply going to have h. Is it okay with everybody? Exactly follow the same, procedure.
Yes, sir.
Fine. So
Yes, sir.
this is going to give me a kh squared. Okay. So if I similarly proceed in this way, then I can get the general term, and which is going to give you will see that your ynx minus yn minus 1x. So that is going to be less than kh to the power n minus 1. Okay. So on Monday's class, I'll do the remaining stuff. Okay. So I'll meet you on not Monday, Tuesday, right? I'll meet you on Tuesday. Okay. Thanks.
Thank you, sir.
Thank you.